All right, guys, so for today's lesson, we're going to be looking at how we solve what's called a linear quadratic system. All right, so we had spent a lot of time back in, I guess, December or January solving systems of equations, right, where we'd have our linear equation, we'd have our other linear equation, and we were concerned with the point of intersection. And we said the unique thing about the point of intersection was that it would be the solution to both equations. In other words, it was the only, each equation on its own had infinite solutions, but the point of intersection is the only ordered pair that would satisfy both equations. And we call that the solution. Now, what we can also have is we can have a linear quadratic system. In other words, we can have a quadratic equation with a linear equation. And again, we're going to be looking for the point, or in some cases, points of intersection. So here's our vocabulary, right? As you can see, it's got a linear equation, it's got a quadratic equation, and consistent with what we know about systems of equations, it would be the point or points where they intersect. So we see it says solution or solutions. So sometimes we'll have one, sometimes we'll have two, sometimes we'll have none. So the example that's listed here has two solutions, right? In this particular system, 5, 8 is going to be one solution that satisfies both the linear and quadratic equation, and negative 3, 0 is going to be the second that satisfies both equations. So just to give you a little sketch for each of them, and again, guys, if this kind of goes too fast, then just kind of pause it and go back and take a look at it, right? So two solutions we already saw, right? So we have got our quadratic equation, and we've got our linear equation, and we're going to have these two nice points of intersection, right? What does one solution look like? Well, one solution can look a lot of different ways. So probably the most common way we can see it is if we've got a vertical line that goes through the vertex. We could also potentially see a horizontal line that goes through the vertex. Or we can have what you guys will learn about in geometry is what's called a point of tangency. So a point of tangency is going to be a point that just touches a curve in one place. So these are three examples of one solution, right? And again, the obvious ones, which usually in class, those are the responses that we elicit, are the vertical line and the horizontal line. But we can also have what we call a tangent line. And then, of course, no solution, I don't think should probably surprise anyone, is that they're never going to intersect. So either we have a horizontal line, or we have, like I drew, a line that's just got a slope that's flat enough that it's never going to meet with our quadratic equation. This would be an example of no solution, right? There's no ordered pairs that will satisfy both. All right, so to get started, we're going to graph our parabola, we're going to graph our line, we're going to see where, if at all, they intersect. So probably it's best to graph the linear equation first, right? So my y-intercept is 3, my slope is 2. And again, I had mentioned before that, this is why when we graph lines, when we graph quadratics, that we want to make sure that we're thorough. Because if I only graph a couple points on my line, a couple points on my parabola, I may not see a point of intersection. So now I need to graph y equals x squared. So I can put it in my calculator. Obviously, this one should be easy enough. And we'll see how far I have to go. And again, I am a little bit limited here as far as what I can graph. So I'm going to certainly graph my vertex. I'm going to graph negative 1, 1, which it looks like is one point of intersection. I'm going to graph 2, 4 and negative 2, 4. All right, and then I'm going to have to go up a little bit more to 3, 9 and negative 3, 9. All right, so if I'm going to connect these points and make a nice parabola there, and I'm going to, of course, label y equals x squared. I'll label my linear equation, y equals 2x plus 3. Now I need to identify my solutions. Now this is a little bit different than solving a quadratic equation because my solutions are ordered pairs, right? Just like when we solved systems of equations, we didn't say x was 3, we said x was 3 and y is 4. So I'm going to identify my two solutions. And then as we did with our linear equations, we could write a little sentence that says the solutions are. And my first solution I've got down there, which is negative 1, 1. And my second solution up here is going to be 3, 9. So those are the two solutions. Those are the 2 points that will check both equations. So if I go to my first equation, right, and I substitute -1 for x and y for y, I get -1 squared is 1 is equal to 1. And if I check -1, 1 with the second one, I get 1 is equal to 2 times -1 plus 3, so 1 is equal to 1. And I also have to check for 3 comma 9. So if I check my first equation, I get 9 is equal to 3 squared, so 9 is equal to 9. And if I check my second equation, I get 9 is equal to 6 plus 3, so 9 is equal to 9. Right, so that's our proof. So again, guys, the connections we want to make here are that with the linear quadratic system, your point or points of intersection are your solutions. What does it mean to have a solution? It means that should check both of our equations. All right, so this is one that I added in recent years because even though the textbook generally doesn't present it this way, on the Regents, they've been asking this a lot, on multiple choice and on short response. And students don't understand that here they're just asking us for the x values, right? So whereas when we solve a system, we're concerned with the x and y values. This one, they just want to know for what values of x will subbing in x for f of x be the same as subbing in for g of x. So it's really a fancy way of saying solve the linear quadratic system. All right, so I'm going to graph my first equation. I'm going to make a table. And as always, we're going to start with our vertex, which should be 1, 1. Which means I should have 0, 2, and 2, 2. And it means I should have 3, 5, and -1, 5. And it means I'm going to have 4, 10, and -2, 10. So I'm out of space up there. I'm just going to fill it in right there. So I think I'll graph my quadratic then now. So I'm going to go down my vertex, which is 1, 1. And then I've got my 0, 2, and I've got my 2, 2. I've got 3, 5, and I've got -1, 5. And I may or may not need to go all the way up to 10, but since I got the space here, I figure I might as well. So that's what my first one is going to look like, and I'm going to label it exactly, and I obviously don't have a whole lot of space here, but I'm going to label f of x, right? It doesn't say y, even though we know f of x is really the same as y. And if I had more space, obviously, guys, I would label it inside, or I'd label it actually on the graph, but this graph's a little bit small. And now we're going to graph the second one using slope-intercept form. So my y-intercept is -2, and my slope is 2. All right, so really, guys, it looks like for this one, I only have one solution. All right, it looks like the only place where this is going to be true, okay, is here. And I'm going to go and label. All right, so if I graph this, which I'm hoping that you guys are doing as well, that's really going to be the only place. This is what I was talking about before. The line is what we call tangent. Now, that's not a vocabulary word you guys need this year. When you study geometry, you'll talk about that a lot, especially with regards to circles. So the solution, right, the ordered pair solution we can look at down here is 2, 2. That's not what they're asking you for. They're saying what values of x. So we'd say only when x is equal to 2. Because if x is equal to 2, when I go to my first equation, I get 2, 2. And with my second equation, it's also going to give me 2, 2. So that's it. That's the only x value. And now, coincidentally, the y value is the same. But it's really, the question is asking us for what values of x is this going to be true, and it will be true when x is equal to 2. All right, so now it says using our calculator. So I don't really have the option here. Obviously, you can't see me, right? I can pull up the calculator, but you're not going to be able to see it. So we're going to think about what happens if we've got something maybe that we can't graph, right? So not that we can't graph it, but positive 18's not going to fit on my 10 by 10 grid. So let's say this was a multiple choice question on your Regents, right? We just want to make sure we can come up with the answer, right? If they gave us a grid, I guess we could go by 2s and we can graph it. So what I want you guys to do is I want you to put this in your calculators. Okay, and again, I don't really have the functionality to use to show you guys my graphing calculator here. But I'm going to give you a rough sketch of what the graph should look like. And again, this is certainly not exactly what it's going to look like, but we know that the coefficient of x squared is negative, meaning that the parabola will open downward, right? It'll appear to be upside down compared to x squared. And we can tell that there's going to be 2 points of intersection, but when I look at my 10 by 10 grid, this point of intersection down here gets cut off, right? So we certainly had talked about things like changing the window. But if we think back to when we did systems of equations the first time around, there were 2 ways we could find the solutions, other than algebraically, using the calculator. We said one was by using the table, and the other was by using the trace feature. Now, if you're going to use the trace feature, you're going to have to change the window. Either that or you're going to have to kind of guesstimate when you pull the cursor down where it's going to end up. So I would use the table. So when I use the table and I scroll down, I end up with one of my solutions is negative 3, 3. So how do we know where the solution is? Well, your x value is going to be negative 3, and you want to know where the 2 y values are going to be the same. So as we scroll down the table, the values get closer together, they get closer together, and then eventually they get to be the same, and then they get further and further apart. So again, guys, you should have been able to see on your calculators by scrolling up the table that when x is negative 3, y is 3 for both equations. And the second one, we should have come up with 7, negative 17. All right, and obviously that's this one here, and that's going to be that one there. So if you scroll down a bit in the calculator again, the values will get closer together and closer together until we get 7, negative 17, at which point they end up getting further apart. All right, so this is what I would do as our work period, as our now try, obviously, right? So same thing, guys. If you're going to do this on your own, at this point, you'd want to pause the video, you'd want to do it, you'd want to unpause it after you're done, and you'd want to check and see what it looks like. All right, so if I was to, when we graph it and we look for the points of intersection, I would expect that our points of intersection should be 2, 3, and 3, 5. All right, if you wanted to try your classwork, guys, and this is not required, okay? Again, when I post the homework assignment is what it is that I want you to send to me, and I'll talk more about that on Google Classroom. This is just if you want some extra practice, right? If you said, well, you did all those examples in class, Mr. Capasso, I want something else that I can work on. You've got some extra work, but this is not something that you need to be submitting, right? That's going to be something separate that will generally come out of the workbook. All right, guys, so any questions or concerns, as always, you let me know via Google Classroom, and we'll have a little discussion about it.